All right, welcome to The Explainer. Today, we're going to dive deep into the world of organic chemistry to uncover the pretty amazing secret life of a family of molecules called alkenes. So let's just jump right in with a question for you. What on earth could a ripening banana, that sweet smell, and the world's most common plastic, polyethylene, possibly have in common? I mean, on the surface, they couldn't be more different, right? Well, the answer is this one. Tiny but hugely important chemical feature, a carbon-carbon double bond. This right here is the heart and soul of an alkene. It's the main character of our story today, and it's what makes them so reactive and so incredibly useful. And really, that reactivity, that's the whole story. An alkene's double bond isn't just some boring structural detail. It is, for all intents and purposes, a big, flashing neon sign that's just screaming, "Hey, over here, come react with me." Now, to really get this, you gotta see them next to their cousins, the alkanes. Alkanes, they've only got single bonds. They're stable, kind of boring chemically, really. They're the unreactive backbones of a lot of molecules. But alkenes? Whoa, that one double bond completely changes the game. It creates what we call a reactive hotspot. It's like the difference between a quiet, empty road and a 6-lane highway interchange. So what's so special about this double bond? Well, it's actually made of two different parts. You've got a strong, stable bond called a sigma bond holding the carbons together. But then you've also got this second, weaker bond called a pi bond. And the best way to picture it is as this exposed cloud of electrons just hanging out above and below the molecule. And that big, juicy cloud of electrons makes it a perfect target for anything that's electron hungry. Okay, so with this big electron-rich target just sitting there, what happens next? Well, that brings us to the main event in the life of an alkene. Because of that pi bond, they don't just swap atoms. Nope, they do something much more interesting. They undergo what's called an addition reaction. That weaker pi bond literally breaks open, and the alkene adds new atoms directly to its structure. In the end, you form two new, much stronger single bonds. And because it's triggered by something that loves electrons, an electrophile, we call this whole process an electrophilic addition. So let's walk through it. First, the alkene's pi bond acts like an attacker, going after an electrophile, let's say a bromine molecule. Then, and this is the key part, the pi bond breaks and a temporary, really unstable thing called a carbocation is formed. Now this step is slow, it's the bottleneck, which means it controls the speed of the whole reaction. We call it the rate-determining step. But once that's done, things happen super fast. A bromide ion, which is now negatively charged, instantly snaps onto that positive carbocation, and bam, step 4, you've got your final product. The double bond is gone, 2 new atoms have been added. Mission complete. Okay, so that's how it works. But why? Why does this happen so easily? Why would an alkene give up its most famous feature, the double bond? It all comes down to one simple thing, stability. This number you see here tells us that the reaction releases a whole bunch of energy. Think of it like a ball sitting at the top of a hill. The alkene is the ball. By reacting, it gets to roll all the way down to the bottom where it's in a much more stable, lower energy state. And nature always prefers going downhill to a more stable place. Okay, that's all fine and good when the alkene is perfectly symmetrical. But what happens when it's not? What if the two carbons in the double bond are different? Suddenly, there's a choice to be made. And it turns out there's a fascinating rule that governs that choice. And that's where Markovnikov's rule comes in. It's actually a pretty simple guideline. When you add something like hydrogen chloride to an unsymmetrical alkene, the hydrogen is going to go to the carbon that already has more hydrogens. You might hear people say the rich get richer, and that's exactly it. The carbon that's already rich in hydrogens gets one more. So this rule predicts that we're mostly going to get one specific product, the major one, and very little, if any, of the other possibility. But why? This isn't magic, it's chemistry. And the reason has everything to do with that temporary carbocation we talked about earlier. And here it is, the why behind the rule. It is all about the stability of that carbocation. Think of that positive charge as being a really heavy weight. The more carbon groups you have attached to that positive carbon, the more shoulders there are to help share the load. These carbon groups are what we call electron donating. They kind of push a little bit of electron density toward that positive charge, spreading it out and making the whole thing way more stable. So, a carbocation with 3 carbon groups attached, a tertiary one, is the most stable. The reaction is always going to take the path of least resistance, the one that forms the most stable intermediate possible. And that path leads directly to the product Markovnikov predicted. So addition reactions are cool, but that's just one trick up the alkene's sleeve. If you use the right chemicals, you can give an alkene a much more drastic makeover. You can oxidize it, and that can literally blow the double bond apart. Now, how this goes down depends entirely on the conditions. If you're gentle, cold conditions, you'll get a mild oxidation. That just breaks the weak pi bond. But if you bring out the heavy machinery, hot, acidic conditions, you get strong oxidation. And this doesn't just break the pi bond, it shatters the entire double bond, sigma and pi, splitting the molecule right in two. Now, you might think, wow, that's destructive. And it is. But that destructive power is actually an incredibly useful tool for chemists. By smashing a big, unknown alkene into smaller, easier-to-identify fragments, they can work backwards. It's like being a chemical detective, using these fragments as puzzle pieces to figure out what the original molecule looked like. Okay, let's try it. Put on your detective hats. Let's say you do this reaction. You start with an unknown alkene, C9H16, and after strong oxidation, the only things you can find are two smaller molecules, propanone and butanoic acid. So, what was the original alkene? It sounds tough, but the logic is pretty straightforward. You just run the reaction in reverse in your head. First, you draw the two product molecules you found. Then, you find the oxygen atoms that were added during the oxidation, and you just erase them. That shows you the two exact carbon atoms that used to be joined together. And for the last step, you just connect those two carbons back together with the double bond. And voila! You've just solved the puzzle and reconstructed the original alkene. Pretty cool, huh? So we've established that the alkene's whole personality is based on its reactive double bond. It turns out that very reactivity gives us a beautifully simple and visual way to spot one in the lab. Yeah, because alkenes are so eager to react, and alkanes, well, they just aren't. We can use this fundamental difference in their character to tell them apart with a test you can see with your own eyes. Here's how it works. Imagine two test tubes. One has an alkane, pentane. The other has an alkene, pent2-ene. You add a few drops of this orange-red bromine solution to both. In the test tube with the alkane, nothing. It just stays orange-red. No reaction. But in the test tube with the alkene, that addition reaction we talked about happens instantly. The alkane gobbles up the bromine, and the orange-red color vanishes. That rapid decolorization is the classic telltale sign that you've got an alkene. So, from the ripening of fruit, to the plastics that are everywhere in our lives, to being a starting point for making complex medicines, that one little double bond is a fundamental building block. Its reactivity isn't a flaw, it's a feature. It's a gateway to creating an almost endless universe of other molecules. So the only real question left is, what should we build with it next?